I like to start in the 2000, 2008, or 2006, 2008 timeframe. A lot of us have left-hand heritage that are at NexGen, and we grew up on the iSCSI scale-out battlefield, you know, the left-hands, the Equalogics of the world, kind of duking it out for what we considered an emerging segment at that time. And at that time, it was really about the mid-range customers getting to their first production-ready VMs. They had virtualization and test and dev. They saw the benefits. They wanted to bring it in production. They couldn't bring it into production unless they had features from VMware, like VMware HA and VMware FT. Those features required a SAN. These customers hadn't yet invested in Fibre Channel, so they went to look to these new architectures, these scale-out iSCSI architectures like left-hand and Equalogic, to meet that need so that they could implement their kind of first round of virtualization in production. So we call that the My First SAN market. And My First SAN was all about lower dollar per gig, iSCSI affordability fit nicely into that category, simple scalability, and all the feature sets that you needed to manage storage, all the data protection, thin provisioning, snapshots, replication. And that was a huge success, as evidenced by Dell purchasing Equalogic and HP purchasing left-hand. That was great, but we're 5 years down the road now. So what's happened in these environments? The problem has shifted. These environments have grown up. It used to be about, you know, I'm implementing virtualization, I need my first SAN. Now it's about, I've virtualized for the last 5 to 7 years. I'm facing different problems than I had back then. It's more about virtual sprawl has caused my storage infrastructure to sprawl. We were just at a customer where I was really surprised by the fact that he had more storage rack U footprint than server rack U footprint. And that's caused a problem for these environments. Not only that, is they're trying to get to virtualization best practice, where they're struggling to get the highest virtual machine density. They want to go from 5 to 7 VMs to 10 to 20 VMs per server. That puts a harder workload on the SAN. Meanwhile, the things left virtualized are the most performance-intensive applications. They're mission-critical, business-critical, or I like to call them the problem child applications. And you know, they're getting pushed to virtualize everything, but they're seeing performance issues today. They've got performance-sensitive applications left to virtualize. That's a problem. So we call this category of problem today my next SAN. So my next SAN is about extreme density, collapsing that storage sprawl, still delivering an affordable solution though, because we are mid-market. You know, we're not selling $100,000 SANs here. The budgets just aren't that high in this segment. And it's all about managing performance, because virtualize randomizes everything. As you guys know, one thing spikes, it impacts everything else. So what we want to deliver with NexGen are 2 key value props. One, deliver more resources in a smaller footprint. That drives down OpEx and collapses your power cooling costs. And also deliver a capability to manage the performance in a shared environment. That's something that we feel the storage industry has missed. All the innovation up to date has been about data protection, capacity utilization, and scale. We've missed the ability to manage a performance resource. So that's what we're trying to go do. So as I alluded to, you know, we sell iSCSI SAN. So just real quick on what we are. The way you break down our box is we've got disk drives in the front, so we're a hybrid SAN. We've got 2 storage processors that are in an active-active configuration, but our solid-state implementation is on the PCIe bus. So that gives us a few different advantages that we'll get into. But the biggest one that you can see up here is that we don't consume any disk drive slots with solid-state. That's a big advantage for the mid-market of who we're selling to. We use Fusion IO today, not necessarily tied to Fusion, but we believe they have the best solution at this time in the marketplace. And of course, PCIe.
So you treat the Fusion IO card as a disk?
As a store. We actually call them stores at that point. A store has a lot of characteristics of it: its speed, its throughput, its IOPS, its redundancy, its data pathing. So we actually call them a store. It can store blocks for us.
All right, but you're using, you know,
it's a disk, not a memory device, right?
Correct. We access it as a block device.
Okay, that's where I'm going.
Yep.
Yeah,
it's
not
a block
memory
device access to us.
Fine. So you could replace it with
That's a very key point of our.
With Veritan, Micron, LSI.
I've seen them all, tested them all out.
I'm sure.
And actually, currently, the Fusion card is actually our choice today. But we've seen them all. We've tested them all out. Some of them have advantages and disadvantages.
Right.
Yeah, definitely. We can go with anything. And the architecture, and you're kind of hitting on a question we're going to get to in a bit. But the architecture doesn't really care. Our product doesn't care what storage it is. We bring it in, we qualify it with some characteristics as I'm describing,
right.
and we can put it into the system anywhere.
Okay.
So we can support anything else. We can actually support them in the same system.
Right.
Okay, along with Fusion IO and solid state, we also have disk. We are a hybrid SAN. The reason that we chose a hybrid SAN is because we are selling to the mid-market. The mid-market has performance-intensive applications along with capacity-intensive applications. They want to consolidate both of those workloads on the same system. That ultimately delivers the most cost-effective operationally and acquisition-wise. So we want to provide as much consolidation as possible. So we have to be good at both. We can't just focus on just performance, and we can't just focus on just capacity. The data path is completely designed around quality of service. So if you look at the software architecture that Kelly's come up with, every single I/O that comes through our system is managed through the quality of service paradigm that we're exposing out for the end users to manage. So it's a filter concept where we categorize all the blocks as their mission critical, business critical, non-critical, and then what quality of service policy they're in so that they can hit a particular performance level. And we'll get into the details on that later. But the key takeaway is that every block goes through those filters, and it's absolutely core to the entire data path of our system. And then, of course, we've got where all of our intellectual property is the software making this work. These are all standard hardware components that we're using. We call our software the I/O control operating environment that has an array of features, dynamic data placement. We do have inline data reduction technology, and we are pursuing patents in that area as well. When we get to a little further in the presentation, if we want to do a deep dive into that would be a fun topic. Performance quality of service, of course, service levels for prioritization, and data protection features all included. So it's very similar to the left-hand equal logic concept. So why do we use PCIe solid state? Again, we're selling to the mid-market. They want as much consolidation as possible. The requirement is be as fast and as high capacity as you can in the smallest footprint. So that's why we chose PCIe. If you look at using a solid-state drive approach, what you're doing is you're unplugging disk drives and you're plugging in solid-state drives. Now we can talk about bottlenecks and all that stuff, but really the inefficiency in this model is that you've consumed your drive capacity slots with solid-state. So you're making a performance capacity trade-off. And if you look at who we're selling to, we don't want our customers to have to make that trade-off. So we've put...
Although I've got a lot more drive slots than I have PCI slots. So, I'm trading off a less valuable resource.
Yeah, that's...
It depends on how you define value, though, Howard. There's a spectrum of capacity versus performance. I mean, right?
Yeah, no.
And to some extent, you are making that trade. But for us, our system has PCIe slots available. As opposed to letting them sit there idle and doing nothing, we can plug solid state in and run with it. So our 3U system has the ability to go with it's actually 4 different cards at PCIe bus speeds. So.
This diagram looks like it has the entire array attached to one read controller, but you've got 2 processors.
So it's actually, it's a super micro storage bridge bay box.
Okay.
It's truly 2 separate compute domains, dual ported SAS.
Okay.
And then inside the compute domains, we can maintain the coherency across them. So
Okay.
who's talking what chunks of drives when. So.
It's a fully active
Yeah.
system, it's not active passive.
Do you have any single points of failure whatsoever in the box?
Good point. No, we don't actually. It's got dual power supplies, redundant CPUs. Drives, as I mentioned, are dual ported.
Well, the SAS backplane, but those don't fail.
Not often, I would say. There is always a chance for a component failure. We haven't seen any failures.
Yes.
Yeah. It's a really, really passive backplane on us.
All right, so a little bit about the data path, how it all works. The key thing is this is our solid state is implemented as a read-write layer. So we want all workloads to contribute, to take advantage of solid-state performance. So any new write that comes into the system gets immediately mirrored across the two processing domains. So we catch it, we make sure it's high availability, we acknowledge back up to the host that we've got your data in a highly available state. Then once we do that, we take, of course, we're consuming half of solid state with redundant data. We don't want to be in that state for long because solid state is an expensive resource. So we move the second copy or the redundancy down to disk and manage it there. Our primary copy remains in solid state so we can continue to do reads and writes as the quality of service policy dictates. If we find that that block is not getting accessed or that block for which the data doesn't need that performance, then we remove that block from solid state, and we're left with the copy in disk. So the way to look at it, everything comes in, lands in solid state, everything, no matter what, and then we start making decisions about what stays in solid state and what gets migrated down to disk. And then, of course, over time, if things heat up or warm up in disk, we're pre-populating the solid state as well to hit those service levels if we need to.
Okay, so the write path is to the solid state disk in the incoming controller mirrored to the doppelganger solid state disk, written down to disk from one of those, which then frees up the solid state in the other?
Correct.
Okay.
I describe it as a temporal mirror. I mirror long enough so that I can get redundancy in HA, push the acknowledgement back up to the initiator, and then I get down to disks, and I can free up the solid state.
And you also you do read cache too. Sorry, Robin.
Yeah. I mean, SSDs aren't that great at small random writes. So, what?
They're better than hard drives, and
Okay.
our system, actually, the SSD sees a contiguous linear workload. It does not see random writes. It doesn't see us jumping all over.
So it's a
Okay.
log structure in the SSD.
Similar to that, yeah. That comes into one of the myths in the industry that solid state has no random seek penalty times, right? It does have one. It's much more reduced than drive. We characterize this, that's part of what I described earlier, we characterize all of the storage systems. So we know what it can do, what it can't do, what can it do for seek, what kind of workload do we need to give it to make it the most efficient workload to it. And then our system takes care of that internally. So really good point. That fusion sees a very linear workload. And it can get ahead of us on its pre-zeroing, as you know they have to do to get ahead of us. So.
Okay, so the statement that all writes go direct to SSD, I guess, is, I mean, there actually is, there's some mediation there that happens in your software before it goes to SSD.
Yeah, all of our QoS engine. Yeah.
Right, okay. 'Cause it was just, I was thinking, gee, it goes direct to SSD, but it doesn't actually go direct to SSD. It actually goes through your software first.
Oh, correct, yes.
Yeah, okay.
But there isn't an NVRAM cache.
There isn't in this model, that's correct.
Okay. So it goes to SSD before it gets ACT.
That's
Right.
correct.
Oh, yeah, sure.
But to the point of the whole architecture, we're actually looking at that now. We're actually looking at a solution with a memory, a battery-backed memory construct.
Right.
The architecture of the software doesn't care. We'll plug it in as a store for us, give it its characteristics. It won't have any random seek penalties at all, which solid state does have some. So we can actually treat it a little bit differently, put those characteristics in, plug in kind of high up in our stack. We can acknowledge at that point while we're cleaning up and coming down to a different store down the line. So.
Yeah, the key point is.
Let me argue against batteries, though.
The system supports what Kelly's saying is it supports any tier of storage device. So whether it's phase change memory, battery back memory, solid state memory, disk memory, any kind of device. And once we know the attributes of that device, we program that into our QoS engine, and now we can basically use it in our QoS model, regardless of what media type it is.
Okay. When the data gets written out to disk, is that also log structure? Or is that more conventional?
It's more conventional. It's more conventional, yeah. We're a thin provisioned back end on the drive, so we got pages, chapters, and volumes, and it's an interesting technology back there for us. So we actually have some pages prepped and ready for new I/O for a volume that's active. But it's a more traditional, almost write anywhere, although we allocate in bigger chunks because they're more efficient than that.
Okay, but it's more a write in free space than a write logical location
Correct.
to physical location.
Correct. Yeah.
And you know, another thing that that we've talked about in terms of the tiering. I just completely lost my train of thought.
Well,
I'll come back to that later.
I got a question.
Yeah.
So, I mean, you know, potentially, especially if you add NVRAM, you're going to be doing, you know, a write comes into the NVRAM, and then it maybe goes to the SSD, and then it goes to the hard drives. So that's a lot of different writes.
We're not saying we're going to implement NVRAM.
Yeah,
This is an example of what we can.
Yeah, but my real question is, so what do you do for data integrity? Because we're talking about a lot of writes here.
CRCs throughout the whole system.
Okay.
Yeah. Comes in, we CRC it, and it flows throughout the system with CRCs.
And then when you read it, you check the CRC.
Yeah.
Okay.
Yeah.
So is
to
that,
your point about lots of writes possibility, part of the QS engine's goal is to land it on the correct storage at the time it's coming in. So it's not an absolute requirement that it kind of trickles down through these. We could actually choose a linear write workload, a big video store. Could skip all of that, drop right down to SAS, because SAS is very effective at that. So we have the ability to do that. Today we're landing most of it in solid state initially.
Yes, and I did remember my point real quick before I forget it again. To Kelly's point on how we're characterizing the different media, it means that we have a variable block size up and down the stack in all of our stores throughout the system. So when it lands in solid state, we're working at a 4K block level. When we're writing out the disk, we're dealing with much bigger chunks because we're sequentializing that workload out the disk. If we did NVRAM, I'm sure we'd characterize the best way to handle that so we get the most out of it. But it is variable block up and down the stack, depending on the tier that we're talking about.